Hey everyone, ready to tackle one of the topics that gives so many SPM students a headache? Yeah, we're talking about rate of reaction. But don't you worry, today we're going to break it all down, make it super simple, and get you ready to absolutely nail these questions on your exam. Let's jump right in.
Okay, but before we really get going, remember, the best way to learn this stuff is to practice it. So after we're done here, you can test yourself with real SPM-style questions. Just scan this code or pop over to the website. It's going to make all of this stick, I promise.
All right, let's be real. You see a graph with a curvy line or a big table full of numbers and your mind just goes blank, right? You feel like you know the theory, but then the question itself just looks so confusing. Sound familiar?
Well, if that's you, you are definitely not alone. But here's the good news. Rate of reaction questions are actually incredibly predictable. By the end of this short explainer, you are going to have a clear, simple strategy to solve them. Let's do this. So, first things first, we have to build a really solid foundation. Let's get crystal clear on what we even mean when we say rate of reaction. Getting this core idea down is the key to everything else.
So, what is it really? The official textbook definition is the change in the quantity of a reactant or product per unit of time. Kind of sounds a bit formal, doesn't it? In simple English, it's just about speed. How fast are your ingredients getting used up, or how fast is your new stuff being made? That's all it is. It's just a speed measurement.
And I love this analogy. Think of it like a road trip. The average rate of reaction is like your average speed for the whole journey. Maybe you drove 400 kilometers in 4 hours. Your average speed was 100 kilometers per hour. But the instantaneous rate, that's your speed at one specific moment. You know, like when a speed camera flashes, at that instant, you might be going 140. Both are speed, just measured differently.
And we see this everywhere in the real world. Some reactions, like fireworks, are incredibly fast. Bam, and they're over. Others, like an iron gate rusting, are super slow. They can take years. Both have a rate of reaction. They're just on completely different ends of the speed scale.
Okay, foundation is set. Now for the fun part. Let's get strategic. You know, the secret to the SPM exam isn't just knowing chemistry. It's knowing how they're going to ask the questions. Think of this as your insider's guide.
I can almost guarantee your exam paper will pull questions from this list. They'll want you to calculate the rate, read a graph, or explain what makes a reaction go faster or slower. Once you see these patterns, they're not scary anymore. You can prepare for them.
Let's kick things off with the one that involves numbers, the calculation. I'm going to give you a really simple, repeatable method that will work every single time. No more guesswork, I promise.
So let's make this real. We're going to use an actual past year question. It asks for the average rate of reaction, but look closely. It says in the second minute. This is a classic little trick they like to use. All right, here's our data. The question asks for the rate in the second minute. Now, here's the trap so many students fall into. They see second minute, and they just look at the 120-second mark. That's wrong. The second minute is the time that passes between the end of the first minute, which is 60 seconds, and the end of the second minute, which is 120 seconds. So we need the data from these two highlighted rows. And here is the foolproof method. It's just 3 steps. Step 1, find the change in whatever you're measuring. In this case, volume. That's just final minus initial. Step 2, find the change in time. Again, final minus initial. And step 3, you just divide the change in volume by the change in time. That's your average rate formula. Easy. So let's plug in the numbers. The change in volume is 26.2 minus 14.5. The change in time is 120 minus 60. This tells us we got 11.7 cubic centimeters of gas over a 60-second period. And when you punch that into your calculator, you get the answer 0.195 cubic centimeters per second. See? When you break it down, it's not so tough. Oh, and always remember to write your units.
Okay, we've nailed the calculations. Now for the second big question type, graphs. A reaction graph isn't just some line on a page. It's literally telling you the story of the reaction speed from start to finish. Let's learn how to read it.
Here's a pretty typical graph you might see. It's showing the total volume of gas that's being produced over time. The key, the whole secret, is to look at the gradient, the steepness of that curve. How steep it is tells you the reaction rate at that exact moment.
So here's what you need to know. Where the curve is steepest, usually right at the beginning, that's where the reaction is fastest. Why? Because you have the most reactants packed together, so they're colliding like crazy. Then, as the curve starts to flatten out, the reaction is slowing down, because the reactants are being used up. And finally, when that line goes completely horizontal,
the reaction is over. It stopped.
But that's a good question to ask yourself. Okay, the line is flat, no more product is being made, but what's actually going on inside that test tube to make it stop?
It's because it ran out of fuel. Simple as that. One of your reactants has been completely used up. We call this the limiting reactant because it's the one that puts a stop to the whole thing. Once it's gone, the reaction can't continue. We're almost there. For this last bit, I want us to put on our examiner hats. Let's look at one of the most common traps that students fall for, so you can see it coming and just step right over it. Okay, this is a huge one. Examiners love to ask questions that mix up the rate of the reaction with the total amount of product. Listen carefully, they are two different things. To make a reaction faster, to increase the rate, you do things like add a catalyst or increase the surface area. But if you want to make more product, at the end of the day, you have to start with more ingredients, specifically more of that limiting reactant. Remember, faster doesn't always mean more.
Okay, that was a lot of info, I know. But we've broken it all down. Let's just quickly summarize everything into a final checklist you can use for your revision.
Here are the 3 main things you need to walk away with. 1. Know that simple formula for average rate. 2. Be able to read the story of a graph. Steep means fast, flat means slow, horizontal means stop. And 3. Remember the science behind it all. Collision theory. The rate is all about how often particles collide successfully. Everything else is just a way to make more of those successful collisions happen.
So as you revise, keep this in mind. It's not just about memorizing facts. It's about understanding the patterns in the questions. You've seen the main patterns today, so you're already way ahead of the game.
So your job isn't done yet. The absolute best thing you can do right now while this is all fresh in your mind is to put it into practice. Go to MCQ SPM. Pick a factor like concentration or temperature and just do a few questions. You've totally got this. Good luck.